Hey, well, today we're going to talk about concentration. So we're going to continue on in Chapter 4, and this is one of the big parts of Chapter 4 is concentration and calculations involving concentration. So we're going to be doing a lot more of the dimensional analysis type things. So concentration is defined as the amount of solute dissolved in a certain amount of solvent. Dilute solutions contain only a small amount of solute, while concentrated solutions contain a large amount of solute. So you can see the diagram here represents a concentrated solution versus a dilute solution, only a small amount of solute. A common method used in chemistry for expressing concentration is molarity. And some concentrations you may be more familiar with like alcohol, for instance, is a percent. So you can do a weight percent or volume percent, like 3.2 weight percent. But in chemistry we mainly use molarity. So the definition of molarity is the moles of solute in exactly 1 liter of solution. And so there's other definitions of things called like molality, and that deals with like kilograms of solvent. And so here's the liters of solution. So your liters of solution means your everything that's put together, everything that's mixed together, the total volume, liters of solution. Molarity can be used as a conversion factor to also find the moles of solute or the volume of solution. But you need to know for the exam, you need to know what the definition, just like molar mass, you know molar mass is grams per mole. You need to know molarity is moles per liter. And it's represented with a capital M. The abbreviation for moles is MOL. So here this problem says, what is the molarity of each of the following solutions? So I have 6 moles of sodium hydroxide, 3 liters of solution. And so I'm given the number of moles here, so I don't have to worry about converting moles. So I just take moles and divide it by liters. So 6 moles, 3 liters. So that would be a 2 molar solution. Just take the number of moles and divide it by the liters of solution. Now this next one says 75 grams of potassium nitrate and 350 milliliters of solution. So again, I need moles divided by liters. So I have to convert my 75 grams of potassium nitrate to moles. You first have to remember what potassium nitrate is. Potassium is K with a positive charge. Nitrate, you have to remember you had to know some of the polyatomic ions. This is one of them. Nitrate is NO3 with a minus charge. And so plus and minus balance each other out. So KNO3s your molecular formula for potassium nitrate. So now we need to find the molar mass of that. So I get my periodic table, look up potassium. So potassium is 39.1. And nitrogen's 14.01. And I take 3 times 16. So I get 101.1 for the molar mass. So grams cancel out and I'll be left my answer in moles. So 75 divided by 101.1, so get 0.74. See if I did 2 significant figures. So 0.74 moles. Now I need to divide that by the number of liters. So I need to convert this to liters, so divide by 1,000. You probably could do that in your head as well, just say 0.35 liters. Okay, so now I have the number of moles and the number of liters. I can find the molarity. So I get 2.1 molar solution. So 2.1 molar solution there. Let's look at this last one, this bottom problem. Now this is how you can use molarity as a conversion factor. So it says what volume of 1.5 molar HCl is needed to provide 6 moles of HCl. So again, you're going to use molarity as a conversion factor. So that's not the number you're going to start with. It's going to be your conversion factor. Your measurement, what you need to know is what volume of that you need to provide 6 moles of HCl. So 6 moles of HCl is where you start. Now remember this M is moles per liter. So I have 6 moles of HCl, I'm going to know what volume. So I've got moles on top here, so I need moles on bottom. So 1.5 moles of HCl per liter. That way my moles cancel out, so I need 4 liters of that solution. So let's go on and work another problem. It says how many grams of KCl would you need to prepare 250 milliliters of a 2 molar KCl solution? So again, my molarity is going to be a conversion factor. So the number I'm going to start out with is the 250 milliliters. I'm going to go ahead and just do that conversion to liters in my head. Remember, it's moles per liter. So to get it to cancel out, I need it in liters. So if I move my decimal point 3 places, 250 milliliters is the same as 0.25 liters. This is moles per liter, so 2 moles KCl. You notice I put that on bottom, but that was moles. So up here is liters, so it wouldn't have canceled out. So I need moles on top here, so liters will cancel out. So that way, my liters of solution cancel out. So now it says how many grams of potassium chloride. So I want to make 250 milliliters of this 2 molar solution. So I'm going into the lab and I need to know how much potassium chloride I need to add to it. So I've got moles of potassium chloride I need to add now. So now I need grams. And to go from moles to grams, you need the molar mass. So 39.1 for potassium. 35.45 for chlorine, 74.55. That way my moles cancel out and I'll be left with my answer in grams. So times that by 2 times 0.25, I get 37.275. And if I look, I need 2 significant figures in my answer, so 37 grams. 2 significant figures here. So 37 grams of KCl. Next one says how many milliliters of a 2 molar sodium hydroxide solution will provide 20 grams of sodium hydroxide. So again, I'm going to start with the measurement I have. The molarity is going to be a conversion factor, so 20 grams of sodium hydroxide is where I start. To be able to use molarity as a conversion factor, I need number of moles because it's moles per liter. So sodium hydroxide is around 40. Let's go ahead and calculate it out. So sodium's 22.99 plus 16 plus 1.08, so 39.998 right to 40. So put the molar mass on bottom. Remember, it's grams per mole, so I put on bottom, so grams would cancel out. Now I asked how many milliliters, so here's where I'm going to use my conversion factor. This is moles per liter. I've got moles on top here, so I need moles on bottom here. So it's 2 moles in a liter. Now it says how many milliliters, so then I need to convert the liters to milliliters. So 1 liter, 1,000 milliliters, and I'll have my answer. So 20 times 1,000 divided by 40 divided by 2. I get 250 milliliters. Two significant figures. There may be sometimes when you're have to make like a 1 molar acid solution, and what you're given is a concentrated solution. So you have to dilute it down to make a certain concentration. So when you add water to a solution, you're making a larger volume of it, but it's not changing the amount of solute that's in there. So the number of moles stay the same. And so we can use this relationship here. So moles of concentrated solution equals moles in your dilute solution. Because you just added water to it, you just diluted it. So if we know our calculations, okay, how can we find moles if we're given a volume, or if a volume's in liters? Okay. My molarity is moles per liter, and so if I take my volume times my concentration, I get the number of moles. And so I can plug that into this equation here, where I know the moles of solute concentrated and moles of solute dilution equation, moles of solute in my dilute solution, and I get what's known as the dilution equation. So this says molarity of your concentrated solution times the volume of your concentrated solution equals the molarity of your dilute solution times the volume of your dilute solution. Or more commonly, it's written M1V1 equals M2V2. And this works for if concentration is expressed in molarity. It also works if concentration is expressed in percent concentration. So let's go ahead and work one of these problems. It says calculate the molarity of a diluted HCl solution made by adding 25 milliliters of a 12 molar HCl solution to water, making 250 milliliters of a diluted solution. So my molarity of my concentrated solution is 12 molar. And my volume of my concentrated solution is 25 milliliters. Now, even though when we solved for and we came up with the dilution equation, we used, you used your volume in liters times your concentration. It actually works in milliliters. You don't have to convert it to liters here. What it must be is that units have to be the same on both sides. So you have 25 milliliters. If you have milliliters, the units of milliliters on this side, you need the units of milliliters on the other side as well. So I'm solving for my diluted solution, and my new volume, my diluted volume, is 250 milliliters. And so this is why your units need to be the same on both sides, because if you solve for MD, your units cancel out. So it could be in liters, it could be in milliliters, and both will work, but they have to be the same on both sides. So if I do that, what is it, 1.2? I get 1.2 molar for my diluted solution. The concept of molarity allows us also to extend the calculations which take place in solution. So we're going to go back and use some stoichiometry, but we're going to use this concept of molarity in our stoichiometrical calculations. So if I look at this, it says what volume of 8.84 molar HBr solution would be required to react completely with 3.62 grams of manganese dioxide according to the following equation. So I'm given my equation, and it looks to be balanced. Yeah, it's balanced. And so where do I start? Where again I'm given a concentration, volume, so it's going to be a conversion factor. So I'm going to start with that measurement. How much is required to react completely with this 3.62 grams? So I want to go from MnO2 to how much of this HBr I need. So to go from one compound to another compound, I need to use a mole ratio for my balanced equation. So to use a mole ratio, I first need to be able to convert this to moles. So manganese 54.94 plus 32 to that 86.94. Okay, so grams cancel out there. Now I can use my balanced equation and see that for every 1 mole of MnO2, it takes 4 moles of HBr. Now the question says, what volume of this 8.84 molar solution do I need? So now I'm going to use that as a conversion factor. I have moles of HBr. So now I can just plug that in. Moles on top here, so I need moles on the bottom down here. So 8.84 moles of HBr per liter of solution. So 3.62 times 4 divided by 86.94. Divided by 8.84. So I get 0.188 liters. So it looks like I need 3 significant figures. So there's 3 significant figures there. Now that's in liters. If I want to put that in milliliters, I could. It doesn't say, it says what volume, so I could leave it in liters. But if you convert it to milliliters, it'd be 18.8 milliliters. Let's look at one more. It says barium sulfate is insoluble in water and can be formed according to the net ionic equation shown. Calculate the volume of 0.5 molar K2SO4 solution that is required to precipitate all the barium from 25 milliliters of 0.35 molar barium nitrate. So where do I start? So I'm going to start, I'm given two different concentrations here. So 0.35 molar. So here I'm given a volume and the concentration. If you're given the volume and the concentration of something, you know you can convert to a number of moles from that. So that's where you're going to start. One where I know the volume and the concentration. So I'm going to go ahead and convert that to liters though, because it's moles per liter, so I'm going to say 0.025. I'm given a net ionic equation. See, it says what the volume of that solution do I need. I'm going to go ahead and there's a couple different ways to do this. You can go ahead and convert this to moles of barium ion, then use your net ionic equation to find your sulfate and convert it back. Or you could write out just your regular molecular equation. So let's go ahead and do that. Let's write out a regular molecular equation. So I have K2SO4 numbering the barium nitrate. So I get barium sulfate, so I take the positive of my first, pair with the negative of the second. Then I get my barium sulfate, which is solid. So again, this is from the previous lesson where we learned about solubility rules. So potassium nitrate, potassium's group 1, so soluble. Barium sulfate, insoluble. If I balance that, I need a 2 in front of my KNO3. So it's balanced now. So it says the volume of the potassium sulfate solution now. So use my balanced equation. Given 0.35 moles of barium nitrate. So my balanced equation is a 1-to-1 ratio for my balanced equation. So now what volume of that do I need? Moles on top here, so moles needs to be on bottom next. So it's 0.5 per liter of your solution. So liters cancel out, moles of barium nitrate cancel out, moles of potassium sulfate cancel out, and I'll be left with my volume of my potassium sulfate that I would need. So you get 0.0175 liters, so if I put that in milliliters, it'd be 17.5 milliliters. So we just went over the dilution equation. Okay. And if you use the dilution equation on this, if you take 25 times 0.35 and divide it by the 0.5, you get the same answer. You get the correct answer. But you should not use the dilution equation to solve these equations. So the dilution equation is made for if you just have the same compound. So the dilution equation, it's HCl, and it's still HCl in. It's not a different compound you're solving for. So in the stoichiometrical calculations, you're going between compounds. So the dilution equation will work if your ratio from your balanced equation is 1 to 1. That's the only time your dilution equation will work. If this is not 1 to 1, you'll end up getting the wrong answer if you try using the dilution equation. So that's going to be it for this video, and so I'm going to wait and save the next video and finish up talking about some more stoichiometry type problems and what in the process is what's known as titrations. So that's it for now.